Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to finally get to that great mysterious topic of chemical reactions. And we aren't going to be restricting ourselves to simple physical transformations. So, we're going to go ahead and start today by looking at a relatively simple type of reaction where I have A going to B. So, this is a simple binary reaction in equilibrium. Everybody's going to be present in the same phase, and I don't have to worry about any stoichiometry. So you can imagine this as maybe something like a simple isomerization reaction. Well, in this case, what we're going to need to first determine in order to evaluate the point of favorability is figuring out where we are in the progression of the reaction. So what we're going to do is make use of the extent of reaction, which is simply going to tell us a lot about how many moles of reaction have occurred. Now, this is worth noting, it's slightly different from moles of reactant consumed or products produced. But in this equivalent, what we can really do is make the simple relationship that, yeah, that's actually fairly true. Because if I have one-to-one stoichiometry, if I'm looking at how much the reaction has changed, essentially this is going to be the same thing as the change in psi, or the change in my extent of reaction. Well, this will actually be equal to the number of moles of A consumed, because for every 1 mole of reaction, I consume 1 mole of A. For every 1 mole of reaction, I produce 1 mole of B. Now, it is worth noting we are going to have to extend this approach to include stoichiometry. So I may have a coefficient for the amount of A consumed and a coefficient for the amount of B produced. And in that case, I can simply get at the number of moles of A consumed by multiplying my stoichiometric coefficient by the extent of reaction. And that's really what um, this is really what our stoichiometric coefficients tell us, is if I have 1 mole of reaction, how many moles of A being consumed or B being produced does this relate to? However, sometimes we like to be able to rearrange these equations and use psi to directly relate to A and B both, in which case we can essentially see a division form. So for every mole of A consumed, it's going to be the moles of A consumed divided by the stoichiometric coefficient to get at how many moles of reaction have actually occurred. And this is one of the reasons why stoichiometric coefficients are so important. We often tend to focus in on this right side of being able to relate moles of A consumed to moles of B produced, but oftentimes it's just as important to be able to relate this to the moles of reaction, especially as the moles of reaction does relate also to properties such as the changes in free energy or enthalpy, which is really one of the most important features for us to focus in on. Because if I want to try and figure out anything about the reactions, I first need to dictate their favorability. And so, not too surprisingly, we're going to evaluate how favorable it is for a reaction to occur by looking at how much the free energy of reaction is going to change if I change the extent of reaction. Say if I go forward by 1 mole or if I go backward by 1 mole, how much will my free energy go up or down? Again, this is a real measure of the favorability. But in order to get at our Gibbs energy of reaction, I first need to be able to come up with a nice, concise equation to describe the change in free energy. Now, again, one of the most important features is since I'm looking at Gibbs, we're going to be assuming constant pressure and temperature. So one way we can illustrate this is by going back to our fundamental equation of chemical thermodynamics, where not too surprisingly, we find that the free energy of reaction is going to be dictated by the change in pressure, temperature, and the number of moles of each constituent component. Now, one of the things we can do is, since I'm looking at the change in free energy, well, I've already confined myself to constant pressure and temperature. So these first two terms will essentially disappear. But that still leaves me with two variables. And this is where extent of reaction essentially kind of comes to the rescue. Because if I'm looking at the reaction of A and B, well, my stoichiometric coefficients are 1 in each case. So simply in this case, the change in the number of moles is related to negative of the extent of reaction, and the change in number of moles of B is related to the extent of reaction. So I can then go ahead and have a simple relationship in between the change in free energy and the extent of reaction, with again piling together my two chemical potentials here. Now, if I go back to the free energy of reaction, well, that's just the change in free energy with the extent of reaction, which, well, all I need to do is pretty much divide out this last term, and we find that the Gibbs free energy of reaction is simply going to be the difference in the chemical potentials of B and A. Where if I have a lower chemical potential for B, well, this is going to tend to give me a negative free energy of reaction, so I'm going to favor product. If the chemical potential of B is greater, then I'm going to end up with a positive free energy of reaction, so this reaction is going to be unfavorable. But one of the things I really want to illustrate here is notice that these are the chemical potentials, not the standard state chemical potentials. So make sure you're cautious, as these chemical potentials are going to change with composition, as we saw with pure species. Because don't forget, due to the fact of entropy, as the system essentially goes to a lower concentration or becomes more dilute, well, then that chemical potential is going to become much lower. And not too surprisingly, we can see this when we look at how the Gibbs energy, this is again our total Gibbs, changes with the extent of reaction. So in this case, I have a species where my products are lower energy than my reactants. And as I proceed along, because products are lower in energy than reactants, it's going to have a negative Gibbs energy of reaction as I go along, until I reach a very critical point where the chemical potential of A and B are equal. Now, why is this the case? Well, because it turns out that if I've got pure B, okay, it's way lower than pure A, but if I put a little bit of A in there, well, then B becomes dilute, and it's a little bit lower in energy and a little bit more favorable. And so as a result, the lowest point on our free energy curve is always going to be some point in between pure products and pure reactants. In general, it tends to be the larger the difference of the two species, the more the extent of reaction tends to look like the lower free energy species. Because again, entropy has less of a contribution than, again, this pure energy difference. Essentially, the dilution effect doesn't matter quite so much. But it turns out that we can also evaluate the favorability of a reaction simply by seeing where we end up on this curve. So if I've got a negative free energy of reaction, this means that I'm going to tend to proceed downhill. And I'm going to essentially go forward. If I have a positive free energy of reaction, well, this tends to mean that I'm going to want to go backwards. And the whole goal of thermodynamics is to try and find what the optimal point is, where I essentially balance which species is lower in energy with essentially this tendency to become as dilute as possible. And we're going to be exploring that idea much more next time as we look at how to determine an equilibrium point. Until then, take care.